Okay, so in the last video, we used inductive reasoning to find patterns and create a rule that makes it easier and faster for us to solve that type of problem. Knowing how to find patterns is helpful in other areas of math and in life in general. In the last video, we explored the relationship between perimeter and area in regular lattice polygons, and we found some very interesting patterns. Mathematicians have also found some very interesting patterns when looking at perimeter and area. So this video will be about some of the historical exploration of perimeter and area. In the 5th century BC, Hippocrates was the first to prove that the area of a circle was related to its diameter, but he wasn't able to calculate what that constant rate was. In the 3rd century BCE, Archimedes used concepts from Euclid's Elements to find what Hippocrates was missing, the value for pi. Not only did Archimedes prove that pi was the constant rate of change between the diameter and the area, but also that pi was the constant rate of change between the diameter and the circumference of a circle, which is a special name for a circle's perimeter. Several hundred years later, in 60 CE, Heron's formula for the area of a triangle was published in the Metrica, a collection of well-known mathematical facts at the time. But some historians believe it's possible that Archimedes knew the formula over 2 centuries earlier. His formula involved taking what he called the semi-perimeter, which was the perimeter divided by 2. It was later discovered that a triangle's area could be much faster calculated using 1/2 base times height, which is not based on the perimeter. But Heron's formula can still be used to find the perimeter when the height is not known. The formula for the area of a quadrilateral was discovered in the 7th century CE, based on a quadrilateral inscribed in a circle. Similar to Heron's formula, this formula is also based on the semi-perimeter. About 1,000 years later, in 1842, 2 different German mathematicians working independent of each other found a way to generalize the previous formula in order to find the area of any quadrilateral, whether or not it was inscribed in a circle. This is one of those formulas. Also, in the 19th century, Gauss was able to use René Descartes' 17th century Cartesian coordinates to develop a surveyor's formula, which can be used to find any polygon area with known vertex locations. Studies in recursion, which began in the 17th century, led to Mandelbrot's 20th century discovery and naming of fractals, which have a very unique relationship between perimeter and area. The mathematician-scientist Stephen Wolfram described fractals as a form of geometric repetition in which smaller and smaller copies of a pattern are successively nested inside each other, so that the same intricate shapes appear no matter how much you zoom into the whole. In other words, a pattern is repeated on top of itself in such a way that the same image appears no matter where you look at it. This video zooms in to a fractal so that you can see the same triangular pattern repeated at any magnification. One type of fractals, known as fractal curves, have a surprising relationship between perimeter and area. With each iteration, the perimeter increases. It actually could go on forever. It has an infinite perimeter, but the area only gets slightly bigger and can never exceed the frame of the original shape. So the area is finite. Mandelbrot called fractals the art of roughness. He proved that many images in nature, which people had believed were rough without any pattern, actually had a fractal pattern. Examples include coastlines, clouds, mountains, and the path of lightning. He was able to prove that these images all have infinite perimeters and finite areas. Here's a picture of the coast of Britain. In the image to the left, someone might think, okay, this is a rough approximation of the perimeter of Britain. But as they zoom in, they realize they could get closer along the edge. And so the middle drawing is made. And that's a larger perimeter. It's closer. But you look at it and realize you could still get even closer into the edges. So then you make the third approximation, and the length, the perimeter, is longer. But you look and see you could still get closer. So you could always get closer. The perimeter of the coast of Britain is infinite. Eventually, we have to stop our approximations and settle for the closest number we can get. But the area only changes a little bit. It has a finite area, but an infinite perimeter. That concludes our exploration of the relationship between perimeter and area. In math and in life, the truth is in the patterns.